Hello all students and welcome to this next edition of our series of revision lectures for physics. So we will continue with this series of lectures which we are doing for the revision of class 11th physics essentials, and the current topic we are discussing within that is vectors and basic calculus. So we have already seen the elements of basic calculus revision in the last 3 lectures. Today is the 4th lecture of the series and we will look at the essential elements of basic calculus. So this is part of this series of vectors and basic calculus revision. So we will begin today by looking at the basics of differentiation first. We will not spend too much time on the derivations and formulae and practice of the mathematical part of differentiation. We will spend more time on the application part and how to use differentiation in various types of situations in physics, not just kinematics but other situations also. But yes, to begin with, we will look at the essential formulae and some of the techniques of differentiation first. So let's start with the concept of rate of change. Okay. So if we have a function of a single variable, where x is what we call the independent variable and y is the dependent variable. Essentially what this statement is telling us is that y, the dependent variable, is a function of x, where the function is some kind of relation between x and y. Typically it is a relation which gives us a unique value of y for every independent value of x, such that y has a unique value for every given value of x. Then we define something called the rate of change of y with respect to x. So we define rate of change in two contexts. Okay. We say there is, first of all, there is something called average rate of change. Something called the average rate of change of y with respect to x, and that will be denoted by a symbol like this, delta y by delta x, okay, which will become nothing but the value of the function at some value x2 minus the value of the function at some value x1 upon x2 minus x1. So this average rate of change is just defined as the change in y divided by the change in x. Okay. So this is the average rate of change from x equal to x1 to x equal to x2. Okay. So for example, suppose we have a simple function like this, that y is equal to, let's say, x cube minus x square, and we want to find the average rate of change, let's say from x equal to 0 to x equal to 1. So we just have to understand here that delta y by delta x will be equal to the value of the function at x equal to 1 minus the value of the function at x equal to 0 upon the change in x, which is this. Okay. So this will, the value of the function will become 1 cube minus, let's make this 2x cube minus, okay. So this is 2 into 1 cube minus 1 square. This is the value of the function at x equal to 1 minus, of course, 0, which is the value of the function at 0, okay, divided by 1. So as you can see, this becomes 2. So the average rate of change's value becomes 2 in this particular case. Same thing if we wanted to find the average rate of change. From, let's say, x equal to 1 to x equal to 4. Okay, now that would be a different value, because we would take x equal to 1 to 4. So this would become the value of the function at 4 minus the value of the function at 1 divided by the change in x. It would be this. So the value of the function at 4, as you can see, will become 2 into 4 cube minus 4 square minus the value at function at 1, which is 2 into 1 cube minus 1 square. So that is your delta y in the numerator divided by delta x in the denominator, which is 4 minus 1. So now you can see that this value here will just become 128 minus 16 minus 1 divided by 3. So 111 by 3. That becomes the value of delta y by delta x, or x equal to 1 to 4. So this is an example of the concept of average rate of change of a function. Now we'll talk about this in the domain of physics also, how this is applicable. Now let's also quickly go over the geometrical interpretation of average rate of change. So if the function y is equal to fx has a graph which looks something like this. Supposing, I'm just saying, we have some kind of arbitrary function. So its graph is a curve like this, y is equal to fx. Okay? And we have selected our points x1 as this one and a point x2 as this one. So correspondingly, the y coordinate at this point is nothing but f of x1, and the y coordinate at this point is nothing but f of x2. So then our our average rate of change becomes nothing but, you will see that it becomes the slope of this particular line that I'm drawing. And this line, as you know, is given the special name of the secant line. So if you see in this line, this interval here is delta y, which is the value of the function at x2 minus the value of the function at x1. And this interval here is delta x, which is x2 minus x1. Okay. So delta y by delta x is nothing but the slope of the secant line drawn joining x1 and x2. Okay, or you can say joining the points x1 comma y1 and x2 comma y2. So it is tan theta for this particular line. This one is called the secant line, and this is nothing but our y2, nothing but our y1. So that is the geometrical interpretation. So in our physics application, both the things are important. The algebraic interpretation as well as the geometric interpretation. All right, so let's look at a couple of examples to understand this better. So for a typical physics example, we could have a situation like this, where we are using the concept that the average speed is defined as the average rate of change of distance covered with respect to time. Okay, so we can define the average speed as delta s by delta t, provided we have defined s as the distance and not displacement. Suppose that's in meters and t is the time in seconds. Then v average would become the average speed in meters per second. So this is the overall definition. Now, given we have a situation where, let's say, a particular problem statement is giving us the distance versus time graph. So it is giving us distance s in meters versus time t in seconds. And this particular graph is, let's say, something like this. So the distance increases linearly from, let's say, 0 to 100 meters in a time of 0 to 20 seconds, and then it becomes constant, remains constant. So we want to find the average speed from, let's say, 10 to 30 seconds. Now, from the time t1 equal to 10 seconds to the time t2 equal to 30 seconds. Okay. So at this stage, you can pause the video and try this question yourself. I will just put up the solution next. So what we want to do is we want to calculate the average speed from 10 to 30 seconds. So that should be nothing but delta s by delta t. This should be nothing but s2 minus s1 upon t2 minus t1, where we should take t1 as 10 seconds, okay, and t2 as 30 seconds. So correspondingly, now we have to find s1, and correspondingly we have to find s2. So this we have to find from the graph. So now let's pay attention to the graph here. So you can see that the time t1, suppose it's this instant here, 10 seconds. So you can see that the corresponding value of s, now from 0 to 20, it's increasing to linearly from 0 to 100 meters. So obviously this will be 50. Okay. And 30 seconds is, let's say, somewhere over here. So the value of s at 30 seconds is this much only. So if this is my t1, then this is my s1. Okay. And if this is my t2, then this is my s2. So I will now substitute that from the graph, and we will get the average velocity as average speed rather as 100 minus 50, the distance covered divided by the time interval of 30 minus 10, that is 20 seconds. So you can see it will come out to be 2.5 meters per second. So this will become my average speed for the interval 10 to 30 seconds. This will become my average speed. Okay, so this is a typical example of the application of the concept of the average speed. Okay, now from this concept, let us move on to the next concept of the instantaneous rate of change. And that is the main idea of interest for us. So from there, we'll see how we use differentiation and the concept of derivative of a function to calculate the instantaneous rate of change. Okay. So instantaneous rate of change of, let's say, y with respect to x, and given that y is the function of the independent variable x. So as you know, this the symbol given to this quantity of instantaneous rate of change is dy by dx, where we understand this as the calculation of a limit that delta x should be tending to 0. It should be very small. Okay. So that becomes basically limit of delta x tending to 0, f of x plus delta x minus fx divided by delta x. Okay. So this is the mathematical meaning of the term instantaneous rate of change. So this dy by dx term, it is called the derivative of y with respect to x, or this operator is called the differentiation operator. And the whole term is called is used to calculate the differentiation of the function fx with respect to the variable x. So this, as you know, is the definition of instantaneous rate of change. Okay. Now let's also discuss about the geometrical interpretation of this first. Then we will come back to the formulae and rules and all that. Okay. So the geometrical interpretation is that when we look at our function, the graphical mode, we plot that two-dimensional graph, which is giving us the variable y as a function of x. And suppose again that graph is represented by this curve. So now what we mean by the instantaneous rate of change is that at some particular point x, we will draw another point which is right adjacent to that one. So that point will have a coordinate right adjacent over here, which is x plus dx. Okay, so if this point here is y, then the adjacent point will have a value of y plus dy. And if we were to join these 2 points by a straight line, because those 2 points are adjacent to each other, they are basically merging into one point. Okay, therefore the line would look like it is just tangential to the curve at that particular point. So it is just touching the curve at that particular point where we are drawing the line. So such a line, as you know, is called the tangent line. The tangent. So the derivative of the function or the instantaneous rate of change. So suppose this is the point x1, so corresponding is the point y1 over here. This just becomes the slope of the tangent. Okay, drawn at the point x equal to x1. So this would be the value of the derivative at x equal to x1. So this would be the instantaneous rate of change. Okay, at x equal to x1. So this is what we call the derivative of the function. So that is the derivative of the function at the point x equal to x1. That would equal to what? It would equal to the slope of the tangent, okay, drawn at that particular point. So this is the meaning of the term instantaneous rate of change. Now to calculate instantaneous rate of change, we have the whole process of differentiation. Okay, so the process of differentiation gives us various set methods and formulae. They're all derived from this basic definition that we've seen earlier, that dy by dx, or the differentiation of the function fx with respect to x, is given by the calculation of this particular limit over here. Now the calculation of this limit using various mathematical techniques which you know as part of your maths gives us a set of formulae. So we will concentrate more on the formulae and the application of formulae for the physics part, rather than the differentiation by first principle, which is the derivation of the formulae using this particular definition. So let's look at the important formulae in differentiation and some of the properties of differentiation. So first and foremost, for the algebraic type of functions where y is expressed as a single power of x, okay, we have differentiation of x to the power n is given by the formula n into x to the power n minus 1, where n could be any real number. So for example, if we are trying to differentiate root x, so we are basically differentiating x to the power half. So we'll just apply this formula. It will be half into x to the power half minus 1, or we can also express this as. So this is the first important formula, which is for the typical algebraic type of functions. Okay. Now, along with this formula, we have certain properties. So for example, the differentiation of a constant is 0, where c is any constant. The differentiation of a constant multiplied by a function becomes the constant multiplied by the derivative of the function. So for example, we want to differentiate, let's say 5x cube. So 5 being a constant, this will become 5 times differentiation of x cube. And then we'll invoke that power rule. So it becomes 5 into 3x to the power 3 minus 1. So as you can see, this will become 15x square. Okay. So this is a simple case of the application of this particular property here. Next up, similarly, we have a property that differentiation of the sum of two functions becomes the sum of their derivatives. So this is sort of a, you can say, distributive property for the sum. So for example, suppose we want to differentiate something like this, x plus 1 by 2 root x. So we want to differentiate this function. So we can express this as root x plus this. Then we can use this principle now over here. We can use this over here. So this will become differentiation of root x by 2 plus differentiation of 1 by 2 root x. Then we can use the principle we used earlier, that the constant multiplied by a function, the constant can be left alone. So it becomes the constant into the derivative of the function. Same thing here, constant into the derivative of 1 by root x, which I can express as x to the power minus half. So in the next step, we can see that this can reduce to plus minus half into x to the power minus half minus 1. So this will reduce to 1 by 4 x to the power minus half minus 1 by 4 x to the power minus 3 by 2, which we can also write as this, or we can even express this a little bit further as x minus 1 by 4 root x. Okay, so hope this calculation is clear. So this derivative comes out to be this finally, after taking the LCM and all that. Okay. So these steps finally here are just algebra. The main thing is the differentiation steps which we have used here and the property of differentiation before this that we've used. Okay, so this is about the basic properties of differentiation. Now, there are a couple of more types of properties of differentiation that we'll discuss. So there is, if we have differentiation of the product of two functions, then it is given by this sort of an operation. It becomes the derivative of the first function multiplied by the second function plus the derivative of the second function, whole thing multiplied by the first function. So we will discuss this with a couple of examples in a bit. Then similarly, we have what we call the quotient rule. If we have the derivative of the division of two functions, then it is given by this formula: the denominator function multiplied by the derivative of the numerator minus numerator into derivative of denominator divided by square. So these are two additional properties of differentiation. Okay, now coming back to some more formulae, important trigonometric function differentiation formulae. So we have derivative of sine x, as you know, is given by cos x. Derivative of cos x is minus sine x. Derivative of tan x is given by sec square x. Okay. Similarly, derivative of cosec x is given by minus cosec x into cot x. The derivative of sec x is given by sec x tan x. And the derivative of cot x is given by minus cosec square x. Okay. And finally, a couple of additional formulae. The derivative of the exponential function is itself, and the derivation of or the derivative of natural log function or log to the base e is given by 1 by x. So this is the complete set of formulae along with the algebraic formula that we discussed earlier of x to the power n. So just take a moment to go through these formulae. I'm sure all of you are aware of these. Okay. So now with these formulae, we will just discuss a couple of examples of differentiation of product and quotient. So for example, if y is equal to x square e raised power x, okay, then find the value of the derivative of y with respect to x at the point x equal to 1. Let's say we want to do this. Okay. So here what we'll do is we'll understand y is some kind of function of x. So first thing we will calculate is dy by dx, which will be the rules of differentiation or the formula of differentiation applied to this function. And this will give us a new function which we can call f prime x. So this function is called the derivative of the function fx, which comes from the differentiation. Now, once you got that, then the value of the derivative at the point x equal to whatever this is, let's say x equal to x1, will be nothing but f prime or x1. So these are the steps that we'll apply over here for this given function. So let's see how we'll proceed here. So the given function is x square e raised power x. So first step, we want to find the derivative of the function. So we have to apply the principles of differentiation to this. Now you can see it's a product of two functions. So we will apply that rule. So it is differentiation of the first function, that is x square, multiplied with the second function, plus differentiation of the second function, whole thing multiplied by the first function. So derivative of x square you can see is 2x, and derivative of e raised power x is e raised power x. So this just becomes 2x plus x square into e raised power x. So that is my derivative. Now we need to calculate the value of the derivative at x equal to 1. So we wanted to find the value of the derivative at x equal to 1. So we will calculate that now as that will just become 2 into 1 plus 1 square into e raised power 1. So that is just 3e. So that is the value. Where e is, approximately 2.7, that exponential number. It's an irrational exponential number. So this is the example of application. Now, for example, let's look at a more practical physics type of application. So we have something like this. Let's take a distance and time problem again. So the distance traveled by a moving body. So the distance traveled, let's say, given by the symbol S, given by the function S is equal to, let us say, 2 root t, where S is distance in meters and t is time, seconds. So we want to calculate the instantaneous velocity the instantaneous speed. Velocity is a vector quantity, so we'll get it to that later. Okay. So we want to calculate the instantaneous speed v at the instant t equal to 4 seconds. Let's say. Okay. At the instant of time t equal to 4 seconds. So the concept that we'll be using here is that the instantaneous speed is defined as the instantaneous rate of change of distance covered with respect to time. So as a formula, we have the instantaneous speed should be this term. It should be the derivative of s with respect to time. Okay. So now all we have to do is apply that concept to this particular function which is given to us. So given this, so here v will be differentiation of this function. So that will just become 2 into half into t to the power minus half. So as you can see, it will be 1 by root t. So the instantaneous instantaneous speed is given by this particular formula now. For this relationship between distance and time, the instantaneous speed with respect to time is given by this relation. Okay, so with that in mind, now we can just substitute the value of time as 4 seconds. So now we can see that therefore, at the instant t equal to 4 seconds, the instantaneous speed is 0.5, and the unit will be meter per second because we have taken s in meters and t in seconds. So that's it. That's simple. So this is the basic type of application of differentiation, particularly in motion related problems, kinematics, etc. Later we'll incorporate vectors into this also. So we'll take parameters like displacement, velocity, acceleration, etc. So in one-dimensional kinematics, for example, you have those relations that the velocity is the rate of change of displacement, the acceleration is the rate of change of velocity. And they become scalar quantities, whereas in general three-dimensional kinematics, they are vector quantities. Okay, so let's move ahead now. Right. So before we look into more interesting applications of differentiation in physics and rate of change in physics, we have to understand another important technique in differentiation, and that is called the chain rule and the differentiation of what we call composite functions. So So these are very standard things as far as your mathematics syllabus is concerned, but also very important for understanding the application of differentiation and rate of change concept in physics. Okay. Be able to execute that application, you must be very thorough and clear about all these techniques from mathematics. Okay, so what is a composite function? A composite function is basically a function of a function. It is a function of a function, that kind of thing. So if y is a function of another function, okay, so for example, if y is suppose square root of sine x, so you can see it is a function of a function, okay, where the first function is sine x and the second function is the square root function. So it operates on gx, so it becomes square root of sine x. Okay. Or another example can be, suppose y is equal to e raised power x cube. Okay. You can see that here the basic function is x cube, and then the composite function is the exponential one. So it is e raised power gx. So it is e raised power x cube. That's what is becoming the value of y. So this type of a function is called a composite function. So now when we differentiate a composite function, we use something called chain rule. So the general method of chain rule is that if y is a function of another function, then first step is we can substitute the inside function or the basic function as a new variable z. Okay. That's like we are introducing a dummy variable. So therefore now y becomes f of that dummy variable. Okay. So this is the substitution step. Now next, the chain rule step. That is like this, that the derivative of y with respect to x can be treated as the derivative of y with respect to the dummy variable multiplied with the derivative of the dummy variable with respect to x. So this is like a chain of operators, so it's called the chain rule. Okay. So in this case, this becomes derivative of this function multiplied with derivative of this function. Okay. So that becomes, suppose the derivative of f is given by the symbol f prime. So f prime z into g prime of x. Okay. And now resubstitute, z was, remember, gx. So ultimately it becomes f prime derivative of the function gx multiplied with the derivative of this. So ultimately dy by dx can also be given by this sort of a direct formula. Or we can understand it by this sort of chain of derivatives. So this is the chain rule. So I'll just leave you with a moment to understand this once. Then we'll look at the applications of this next. Okay, so let's understand this chain rule thing with a couple of examples next. So for example, suppose we have y is equal to sine square x, and we want to find dy by dx, the derivative, and its value at x is equal to, let's say, pi by 6 or 30 degrees. Okay. So here we can understand that y being sine square x, it is a function of a function. Okay. It is whole square of gx, where gx is equal to sine x. Okay. So what we'll do is first we'll substitute sine x becomes our dummy variable z. So y becomes z square. Then next we will apply the chain rule step. It should become like this now, that this is the derivative of y with respect to z multiplied with the derivative of z with respect to x. So next step, this becomes very simple differentiation. So this becomes 2z multiplied by sine x. Now we know that z is equal to sine x. We had substituted that here. So we put that back over here. So this becomes, sorry, the derivative of sine x on the other side will be cos x. So we will also use this as a formula now, that the derivative of sine x we know is cos x. So this now becomes 2 times sine x cos x, or you also know that as a formula it is sine 2x. But more importantly, we got the value of dy by dx. Okay. So that's the first thing that we needed to calculate, which we've done here. So I'll just leave you with a moment to go through this solution. And then we will take a look at the value. So dy by dx at x equal to pi by 6 will become sine of 2 into pi by 6. So that will be root 3 by 2. So that becomes our value. Right, so just take a moment and go through this. We will start with another problem next. Okay, next up, let's look at another example of this application of chain rule. So we have y is equal to square root of x square plus 16, let's say. And we want to find, again, derivative, okay, and its value, let's say at x equal to 3. So once again, you can see over here that the function y is equal to square root of x square plus 16. It is like square root of gx, where gx is x square plus 16. So it is a composite function. Y is f of gx, where it's this and this is this. Okay. So we will use the chain rule method. So the first step is the substitution method. So x square plus 16 becomes our dummy variable z, and therefore y becomes square root of z, or z to the power half. Then we have our chain rule step, where the derivative with respect to x is the derivative with respect to z multiplied by derivative of z with respect to x. So this becomes differentiation of z to the power half, which is very easy differentiation. And this becomes differentiation of x square plus 16, which is an equally easy differentiation. So next step, this term becomes 1 by 2 into z to the power minus half, and this term becomes 2x. So ultimately we are left with x by root z, which is ultimately x upon square root of x square plus 16. So this is our derivative now. This is what we are looking for in the first place. Okay. And then of course, to find the value of the derivative at a particular value of x, we have to just substitute. So now at the value x equal to 3, the derivative at x equal to 3 will just become square root of this, which will become 3 by 5, as you can see. That's our numerical value. Okay, so these are a couple of applications of chain rule, which, as I told you, are very important in physics. Now we will see a more sort of physical example of the application of chain rule. We'll discuss next. Okay, so once we have this concept of chain rule understood now we can see the really interesting type of applications of differentiation and rate of change in physics, and we can understand the whole range of applications also, the various different methods. So let's look at an example of something called the constraint relation concept in mechanics, and an example of application of differentiation in that. Okay. So for example, suppose we have a physical situation like this, where we have a block placed on a frictionless surface. Tied to a thread. Okay, so let's look at the situation. So we have this block which is tied by a thread like this. So this is a massless thread, or it's a light thread. And this block is movable on this smooth surface. Now suppose what is happening is an external agent is pulling this point, the point A on the rope. It's being pulled down at some speed. V naught. Okay. So the end A of the thread is being pulled down at a uniform speed V naught equal to, let's say, 2.4 centimeters per second. So now we want to find the speed with which the block will be moving. Find the speed of the block at an instant when theta is equal to 37 degrees. Okay. And also find d theta by dt. That is the rate at which the angle of inclination of the thread is changing. This angle with respect to the horizontal is changing. Okay, this is what we want to calculate over here. Okay, so let's try to understand this situation in detail here. So what's happening is, as you're pulling the point A down, the block is going to get pulled towards the right because its weight is going to keep it on the floor, okay, on the smooth horizontal surface. But the motion will be in such a way that the thread length will remain constant. Okay, so we will use that to solve the problem dynamically, or we'll use that to solve the relationship between the motion of the block and the motion of that point P. Okay. So if this is the situation at some particular time T, now let's say after a bit of time, the block would have moved to a position like this, okay, and the thread would have changed its situation to this now. So you can see that theta is increasing, okay, while if you take this distance to be y, so now this is increasing to y plus delta y, while this is, if this thread length here was, let's say, z, then this thread length here is becoming z minus delta z. So this is what is happening dynamically. Now, how we can express this in terms of calculus, let's understand this. So first of all, what we have to understand is that the thread length is constant. Okay. So whether we look in the first picture, it is z plus y, that is a fixed thread length, or we look in the second picture where it has reduced to z minus delta z, but this one is increased to y plus delta y, that must remain constant. So comparing these two relations, you can see that the increase in length on this side must be equal to the decrease in length on the other side. So this is what we are going to use to find out the relationship between V and V naught next. So now let's see how we can set this up by the calculus method. So this hypotenuse over here for us was Z, the thread length which is part of the hypotenuse. This we have taken as Z, and this we have taken as Y. Okay. Now additionally what we can, and we have Z plus Y is a constant thread length. That is the important thing that we'll be using over here. Now further see what is happening is that we have defined the velocity of the block along this axis. We have defined it as V, and the velocity of the point A in the downward direction, we have defined it as V naught. Okay. So we can further say that if we drop a perpendicular from here, and we draw a right angle triangle like this. So if we take this distance as a fixed height, okay, because this is a fixed height, okay, and we take this distance from here to here as x, and of course this distance here is y, whereas this distance was z. So further we can now define that if you see in terms of calculus, v is equal to minus of dx by dt, because x is decreasing at the rate of, x is the distance between this block and this fixed point over here. That point is not moving because the pulley is fixed. So x is decreasing at the rate of v, whereas on the other hand, v naught is equal to plus of dy by dt, because the thread length on this side y, it is increasing at the rate of v naught. Okay, so these are two things that we can utilize over here. So next thing what we want to do is to find the relation between v and v naught. We will have to find the relationship between z, x and y using this relation. Now further here you can see that z is equal to square root of x square plus h square, where h is a constant. This height of the pulley from the ground, that's not changing. X is varying. It's a variable such that I have seen dx by dt is this. So my constraint relation now will further become like this, that square root of x square plus h square plus y is a constant. This is the thread length. My constraint relation, which was z plus y, that will reduce to this. Now to this we will now apply differentiation principle. So just make sure you understood up to this step. Now we'll see how we can use the differentiation principle to apply this. Okay, so next up you will see that when we apply the differentiation principle, differentiation of the whole left hand side, which is square root of x square plus h square plus y, is on this other side differentiation of a constant. So that is 0. Okay, so differentiation of square root of x square plus h square, we can now open this bracket and apply the distributive property of differentiation. So that should be on the other side 0, because differentiation of any constant is 0. Okay. Now here to calculate this term, now we will now use chain rule. We will use chain rule. Okay. So we will see that differentiation with respect to time of the function x square plus h square, the power half. We can write this as differentiation with respect to x of the same function multiplied with dx by dt. And further this will become 1 by 2 into x square plus h square to the power minus half into 2x, like the differentiation we had seen earlier, okay, into now this term dx by dt. So this will ultimately become x upon square root of x square plus h square, whole thing into dx by dt. So this term will become this term. So we'll resubstitute this here next. So we'll see this becomes x upon, see this becomes x upon square root of x square plus h square into dx by dt, okay, plus dy by dt is equal to 0. So this is what the application of chain rule and differentiation is telling us now. Okay. Now we will understand once again that the rate of change dx by dt is minus v and the rate of change dy by dt is plus v naught. So we will plug in these two values here, and that will give us the relationship that x upon square root of x square plus h square into minus v plus v naught is equal to 0. So we have or we can also write that as V into x by z. Now going back to your diagram, you will see that that x by z was nothing but cos theta. Sorry, not this term was nothing but cos theta. So coming back here, you can see that x by z is nothing but cos theta. So we have this relation that V naught is equal to V cos theta. So this becomes the constraint relation, the so-called constraint relation between V naught and theta. The constraint being what, that the thread length is constant. So in our question, it was given to us that V naught was a constant value of 2.4 centimeters per second, and we wanted to find out at the instant when theta is 37 degrees. Okay, so V naught was 2.4 centimeters per second, and we wanted to find out V at the instant when theta is equal to 37 degrees. So V will become V naught sec theta. So in this case, 2.4 centimeters per second into sec 37. Okay, so this becomes the instantaneous velocity, as you can see. Okay, so that was the first part of the question. Now we also wanted to find out the rate of change of theta. So for that, we have one more constraint relation, as you can see. So we have the constraint relation that this distance was x, which was changing with time. This angle was theta, okay, and this was a fixed length h. So we can express over here tan theta as h by x, or even better, we can express cot theta as x by h. Okay. So now if I differentiate this equation on both the sides, so differentiation of cot theta will give us differentiation with respect to time of x by h. Okay. Now again, to differentiate cot theta with respect to time, I will have to use chain rule. Okay. So I will use the chain rule that differentiation with respect to time of cot theta will become differentiation with respect to theta into d theta by dt. And as per my formula, differentiation of cot theta is minus cosec square theta. So this side of the equation will become this. So minus cosec square theta into d theta by dt. And on the other side, I can take 1 by h outside because it's a constant and just multiply with dx by dt. Okay. Now dx by dt is nothing but minus v. Okay. Dx by dt was minus v. So we saw that when theta was 37 degrees, okay, v turned out to be 3 centimeters per second. So just substituting that relationship here now, we will get that minus cosec square 37 degrees into d theta by dt is equal to 1 by h into 3. So d theta, of course, this is minus 3. So this should be substituted with minus v. So minus 3. Okay, so the minus sign cancels out, and we get d theta by dt as 3 upon h into sine square 37, which is 3 divided by h into 3 by 5 whole square. Okay. So we will get the value of that d theta by dt in terms of h, which means that we need to know the value of that height in order to be able to determine the exact value of d theta by dt. But this is the relationship. So suppose h is, let's say h is some 20 centimeters or something. Then d theta by dt at that particular instant radians per second, this will come. So this will become the value. So this is another example of the typical application of chain rule for the constraint relation. Okay, this is again the constraint relation that we are getting. This is the constraint relation between the quantity v and the quantity d theta by dt and the instantaneous value of theta. Okay, so these are the applications of differentiation. Next up, we will look at the basics of integration and the applications of integration in physics. Okay. So you need to be clear about the rules of differentiation and some of the techniques of the application of chain rule and differentiation, because most of the time the application of differentiation in physics also has to do with constraint relations, which are of this type, where we need to use the chain rule, because we are looking at rate of change of one quantity with respect to another, like how theta depends on x, and then how x depends on time. So then from that we are relating how theta is changing with respect to time. So there is an application of chain rule like we've done over here. So make sure to keep these things in mind when you're looking at the applications of differentiation and rate of change in physics.